Hello student, welcome to tutorial 1B, still in single condensable component. Okay, now we are going to use single condensable component concept in mass balance. Okay, so I still use the example 6.3-2 from textbook. Okay, the question sounds like this. A stream of air at 100 degrees C and 5,260 millimeter mercury contains 10% water by volume. Calculate the percentage of vapor that condenses and final composition of the gas phase if air is cooled to 80 degrees C at constant pressure. So this question is if we interpret this question into a picture, process flow diagram, so it looks like this. Okay, so we take a basis. Let's say the basis is 100 mole feed gas. This feed gas is 100 mole. So because it say condensation, so it goes to condenser lah. So the unit operation is condenser. What it wants is actually this stream of air put into condenser, and then some part of the gas will become liquid and some will still remain in vapor. That's what happened. This is what this question actually implies. Okay, so we have basis 100 mole field of gas. So now we will draw the process flow diagram. So we have a feed inlet. We have feed inlet to a condenser. This is the stream. Okay, so we have 100 moles, so because it gives 10% water by volume, so we have 0.1% is water, 0.1 water and 0.9 are dry air. 0.9 is dry air at system temperature 100 degrees C, pressure at 5260 millimeter mercury. If we remember, this stream just now contains water vapor at superheated stream, a superheated state. Remember? So these are superheated state. Okay, superheated state. Right, and then this superheated state gas is put into condenser where this gas will be condensed at 80 degrees C. So from 100 degrees C inlet, it will be cooled to 80 degrees C. So definitely some parts of the single condensable contained in this gas will become liquid. So the one previously from the previous tutorial, we know that the single condensable component in this gas is actually water. So definitely some parts of water will be cooled and become liquid. So this is the stream for that liquid. And some parts of it will still remain in gas. Okay? So if we remember previously, to make this superheated state become superheated vapor become saturated vapor, so it has to be cooled at constant pressure at 19 degrees C. If you cool this line at 90 degrees C, which is at the dew point at the constant pressure of 5260 millimeter mercury, the first liquid drop will form. But the question say air is cooled to 80 degrees C at constant pressure, where it is cooled at constant pressure but cooled to 80 degrees C, which is lower than dew point. Therefore, it's not just the first drop, but we probably will see more drops of liquid will be formed here instead of first drop, because the temperature, it is lower than dew point. This is the first drop, but if you cool to 80 degrees C, that means you're expecting more water vapor will become liquid here. So, but what will be the, so if a condenser, then you'll have one line for liquid, which has become liquid from condensation, and then you'll still have remaining gas. We expect to have remaining gas in terms of, and the composition will be in terms of water vapor and also dry air. Okay, this is gas. So I put it put it vapor here. Okay, right. So now this is how the process flow diagram looks like. So in order to, the question wants you to calculate the percentage of vapor that condenses and to find final composition of the gas if air is cooled to 80 degrees C at constant pressure. This is the process flow diagram. So we need to find, in order to calculate the percentage of vapor that condense, we have to find we have to find this first. This and this first. Then we can calculate the percentage. So in order to solve this question, we need to find the composition of the gas phase. This is the gas phase here, right? So to find the composition at this gas, to find the composition of a gas phase, so we use Raoult's law. Okay, we can find, because this is gas. Okay, this is gas. We can use Raoult's law, where there is Raoult's law in equilibrium, where we relate mole fraction of gas with the vapor pressure. Okay, we use this equation, so we can find the vapor the mole fraction of water here. So we use this Raoult's law equation because we know the temperature of the system at the outlet is 80 degrees C with pressure 5260. So we can find, using this equation, we can find mole fraction of water here. Because all this system is gas liquid in equilibrium. So we can apply this equation of Raoult's law. Okay? So to find mole fraction, we remember Raoult's law, single condensable, where we have this equation. So we know we have a pressure and also T, so we just plot in, and then we'll obtain our mole fraction of water here as 0.06753 mole water per mole. Sorry, this should be changed to W instead of H2O, yeah, because our water is actually W here, not H2O. So this is actually W, yeah. So this is the composition of water. So you know, this information are from table B for Antoine equation, because this equation is actually Antoine equation. So this value here is actually P of the system. So you have the temperature of the system. So you obtain your mole fraction for water, the single condensable component in this part, water. This is the mole fraction. So once you know the mole fraction of water, you can find mole fraction of dry air, because this line, this outlet for gas here, only contains water and dry air. So you just take 1 minus y, because you already obtained this y. So you'll get the composition for a dry air in terms of mole, that is 0.9325 mole of, dry air. This is dry air, dA per mole, yeah? Dry air per mole. So you know, these are the composition of your outlet gas, DNV. Okay, let's look how we find the next thing that the question wants, the percentage of vapor that condenses. Okay, we write down the information just now, because the information just now. So we know the mole fraction of water is this much at the outlet, and the mole fraction of dry air at the outlet gas line is this. Okay, now we are now going to find the percentage of vapor that condenses. The percentage of vapor that condenses. Percentage of vapor that condenses. This vapor here refers to water vapor. Percentage of water vapor that condenses. That means they want to find, if it says like that, it means the vapor percentage of vapor condenses means how much of the liquid form divided by water at feed line. How much liquid form? This one divide by how much water that goes into condenser. That's what it means by percentage of vapor that condenses. So this is the thing that they want to find. Okay, percentage, yeah, so times by 100. So in order to find an L, you need to get an L is to, first of all, we have to find this first. Okay, so dry air balance. If we do dry air balance, we will obtain the information, the number of mole for vapor here, the outlet vapor here. Okay, dry air balance, you'll get the number of mole of vapor here. So because dry air only involves in two line, feed line and also gas line, outlet gas line, vapor line here. So 0.9 times by 100 in equivalent to mole fraction here times by NV, then you get NV, this mole is 96.51. Okay, from here then you use the overall balance. You use the overall balance, then you obtain NL. Okay, because 100 moles that goes in plus equivalent to NV plus NL, NV plus NL, right? Then you obtain your liquid form. This is water liquid form. From this, it becomes this, water liquid form. So it is 3.49 moles. So the liquid that form is 3.49 mole water. Okay? So once you obtain this, then you can find the percentage of vapor, because percentage of vapor is NL divided by water feed times 100. So you just take this NL value, goes here, divide by water inlet, water vapor inlet just now, and then you use this formula, you obtain the percentage of vapor that condenses is 34.9%. So it says that from water vapor that goes in, how much of it? 34.9 actually has become liquid. That's what it meant. So it has part 2, where in this question we cool the system. We cool the system, but at constant P. For this question, we condense the water vapor by reducing temperature, maintaining P at the same pressure. Pressure in and out is the same. But I would like you to go to part B, part 3 of this question, where we do condensation. We change a mole into liquid. Water vapor into liquid using compression. So I want you to go look at the example by yourself and try to understand it. Yeah. So in the second part is actually more on compression, where you increase pressure, but increase pressure at constant T. Alright. So thank you for watching. I hope you understand this example using single condensable component concept in mass balance. Thank you.